in class 10 we will be going to study two types of lenses, which is convex lens, another is concave lens. Okay, convex in this is called double convex lens, and this is double concave lens. Okay, so concave lens. Okay, now normally we do not use this term double most of the times. Simply we call it as convex lens and we call it concave lens. Now convex, here the refracting part of the lens is bulged out from both the sides. Okay, it doesn't look good in here. Let me make it again. Let's see about the convex lens first of all. Now one is bulged out, one part, another part is bulged out, so this is a convex lens. Okay, now the size of the lens is called its aperture. Okay, this is known as the aperture. So aperture is basically the size of the lens. The midpoint of the aperture is known as the optic center. Optic center, we denote it as O. Okay, so what is O is? It is an optic center. Okay, now an axis passing through the optic center, just like we did in a mirror, this is known as the principal axis. Okay, then now the lens, as it is made up of two spherical parts, okay, that's why there will be two centers on the left and on the right. Okay, on the left, we called it as 2f1. Okay, it is same as that of C1. Okay, these are the same, means center. C stands for center, and right in between O and F there is focus. Okay, there is focus, as there are two focus. This is called F1C. F1 is half of that of the center of the spherical lens. So this in place of C1, normally we call it 2f1. It's double of it. Okay, and you need to remember this f1 is the midpoint of 2f1 and O. Exactly in the same way you have to make at the same distance on the right side 2f2. Okay, so this we are learning how to make the different parts of the lens. Now it's on the right side, so we use it as 2f2. Okay, and this is as f2. Okay, I think it's clear now. All right, then these are the focus. So how many focus are there? Two focus in case of lens. Okay, f1 and f2, and two centers. Okay, 2f2 is also known as the C2. Okay, C1 and C2. These are the parts of the lens. Now coming similarly, the same thing holds even true for the concave lens also. In case of concave lens, the inward part is the concave, right? All right, then this is known as the aperture of the mirror. Aperture, I'm not making it properly. Okay, then the axis passing through this center is known as the optic center. The axis passing through the optic center is known as a principal axis. Then on both the sides there are two focus, that is what, f2 on the right side, f1 is on the left side, and double to that of it, 2f1 and what to say, 2f2. Okay, now in case of lens, refraction occurs, right? Okay, And the refraction has some rules which you need to know in order to make the ray diagram. Okay, now object, in case of in case of lens, we always keep the object on the left. Okay, so this is a rule you need to know. Object has to be on the left side, not on the right side. Okay, now let us quickly learn about the rules about how to make the ray diagram. Okay, now coming about the first rule. Okay, the first rule is very easy. A ray parallel to the principal axis, okay, ray, the incident ray parallel to the principal axis on refraction should pass through the second focus. Okay, so this is the incident ray. Okay, this is the incident ray, and this is what? This is the refracted ray. Okay, so we need to remember refracted ray. The incident ray, which is parallel to the principal axis, this have to be parallel. Okay, then on refraction it should pass through the second focus. Okay, another rule number 2. Rule number 2, it says, let me use the other color to be more clear about it. If a ray is passing through the optic center, then it should pass undeviated. All right, now this incident ray, if it is passing through the optic center, then what to say, it should pass undeviated. So if you are using these two rules in case of convex lens, you will be able to make all types of ray diagram. Okay, we will take one example and later on we will study in detail. Okay, let's see. Okay, let's see. Give me a little time. Okay, let's see. Here is a lens, convex lens. Okay, how to make it? You will make equal curve on both the side. Then you will make the aperture as a dotted lines. Then you will, the center of it is the optic center. You will denote it as O. Then you will make the, what to say, principal axis. Then on equal lengths, you are going, first of all, you are going to choose 2f1. Then midpoint of it f1. The same distance you have to choose on the right side also, that is what, 2f2, and the midpoint of it is f2. If you remember these things, then it's okay. Now at some position, let us keep the object. Okay, now the object, where we need to keep, always on the left side. This is by convention. Okay, let's see. We have kept the object somewhere here. Okay, let's say the object is at here. Let's see, this is the object. Okay, this is the object somewhere here. Now let's make the ray diagram for it. Okay, now if in order to make the ray diagram, we always choose the tip of the object. Okay, now let us apply the rules. Rule number 1, what? From the tip of the object, a ray which is parallel to the principal axis, right, it should pass through the focus on refraction. Clear? Right? Fine. Then from the tip, again, 2 minimum refracted rays we need to have in order to make the image, right? So another, an incident ray passing through the optic center will pass what? Undeviated, right? It should pass where? It should pass undeviated, right? Now this is the point where the 2 refracted rays are meeting, and this will be what? This is the head of the image, and we get the image. All right, fine or not? All right, so this is the image. Now how the image looks? The image looks what? inverted. Inverted means what? Upside down, right? Where the image is on the other side, right? The refracted rays are really meeting, right? So always inverted image is real. Okay, this we need to keep in mind. Okay, then how the image is bigger, smaller, all these things, all the character of the image, we need to write it. Okay, clear? So this way, when you apply the rules, you will be able to get the image of the, you will be able to get the object's image. Okay, then just like a concave mirror, you have you should know some of the things. Okay, let me do it quickly. Like I'll make it again because convex lens is, it is in detail. Optic center, principal axis, I'm making manually, roughly 2f1. Okay, f1, then where it is f2, and this is 2f2, right? Okay, where we can keep the objects. Okay, we can keep the object beyond the center. 2f1 is same as that of the center, right? We can keep beyond c1, right? Very far from c1, we called it at infinity. We can keep at here. We can keep between c1 and f1. We can keep at f1. We can keep between the optic center and f1. So at different positions, being the spherical lens, the images will be different. Okay, now I will start up with infinity. Okay, infinity means what? Very far away as compared to this aperture of the lens. Okay, when the object, okay, let me use the blue, what to say, let me use the blue color for image. Okay, if the object is very far away, let me call it very far away, where the image should be, for very far away, the image should be at the focus point size. Very far away, image will be at the focus. I think in your childhood days, you used to focus the sun rays and burn the paper, right? What you are, the sun is at infinity. Using the lens, you are trying to make the image of the sun on the paper. And as this, as the image of the sun is formed on the paper and the paper got burned. Okay, so this is an this is a this is quite relevant, right? Okay, now as the object approaches nearer the center of the lens, okay, the image of it will be shifting towards the right side of the center with increase in size. Okay, like from infinity, at infinity, the image will be at the focus point size. As the object is approaching nearer, the image of it will be shifting away from f2, increase in size. The same object you are bringing here, let's say. Okay, now what will be? The image will be further shifted towards this, in this case what? Increase in the size, still inverted. Okay, you bring it further here, you're bringing it nearer, still the image is shifting away. All right, increase in size. All the time you see the sizes increase as compared to the previous, right? And when the object is exactly at the center c1, the image of it should be at where? At c2, same in size. Okay, fine. So if the height of the object is 1 meter, the image height also have to be what? 1 meter. Now the image, you have seen its size is increasing. At c2, it reached to the same height of that of the object. Now if you are bringing it further close, okay, same object, the image will be shifting further away with the increase in the size. Okay, shifting object is moving towards the focus, the image is moving away from the center, increase in size. So what happened? Till C1, the image is small at for object C1, image at C2 exact in size. But later on, what? The image of it gets bigger and bigger and bigger. All right. And there comes a point where at F1, where the object is at the focus, the image will be very, very big. We call it infinity. All right. We call this one infinity, very, very far away. Understood? Okay. Now, now there comes an exceptional case. When the object is between optic center and F1. In this case, if the object is kept between the focus and the optic center, then its image, okay, its image will be on the same side and it will be bigger. So this case is an it is an exceptional case. Okay, we will see it. Exceptional case. Okay, I will repeat it from the beginning. Okay, for very far away object, the image will be at the focus. As the object approaches nearer and nearer, the image of it will be shifted towards the C2. Okay, with the increase in size. For C1, the image will be at C2 exactly in same size. As it increases, as the object approaches towards F1, the image of it heads away from C2, increase in the size. At F1, the image will be very, very bigger at infinity. There comes an exceptional case where the image of it will be on the same size. Okay, we will see this exceptional case. Similarly, the same thing will hold for the it will be holding same for the concave lens also. Let's see it once. Okay, for concave lens, concave lens is known as a diverging lens because it diverges the light ray. Okay, so this is an aperture. I'll quickly do this one. Okay, then this is an optic center. Now if the here also there are same things like F1 and 2F1, then F2 and 2F2. Now 2F2. Okay, all right. Then where this is the concave lens is a diverging lens. So wherever your object is, suppose the object is here, it diverges the light rays, but when you produce it backward, it meets at the focus, but on the other side. All right. Now another is the light ray passing through the optic center, it remains the same. All right. Okay. So the one difference you need to know, convex lens is converging lens, while concave lens is diverging lens, because it is diverging the light rays. Okay, it is diverging the light rays. Now for concave lens, all the time the image will be smaller and it will be on the same side. Okay, we will see it. Okay, like in this case, okay, let me make it again. Concave lens, somewhere we are keeping the object, F1, F2, the rest of it I'm not showing it. Okay, wherever you keep the object, suppose I have kept the object here, then what will happen? It will diverge it out, we produce it backward, meets at the focus, then another pass through this, where the two refracted light meets here, right or not? So where the image of this object is, the image of this object is here. So how the image is the image is small, diminish. It is virtual because it is produced by the dotted lines. This is the real refracted rays. It is produced, so this is virtual. When it is virtual, it is erect. So for concave lens, all the time the image is diminish, virtual, and erect. Okay, so you can see the text in detail about it. Let's see the what to say, convex lens quickly. Okay, let me keep the convex lens. Okay, I'll tell you the trick also while making it. Okay, so this is f1, let me call 2f1, let me call same equal, it have to be. Okay, students, be careful while making it. 2, then this is 2f2. All right, now if the object is here, where the image of it should be, I'm talking about the trick. Okay, you need to know where the position of the image have to be. For this f1, the image should be equal length, equal in size, right? Now make the ray diagram. Okay, now make the ray diagram. From where it should pass? Should pass. Oh, you have to adjust it. Okay, otherwise this way it will never come. Another. You have to make this way. So came now. So first make the image, thereafter you do for this 2f1 position. Okay, particularly. Now if the object, now I'll take that exceptional case because that is little bit okay. It is ray diagram consume time. Okay, I have to do again. Students, see the textbook. The textbook will give you in detail, in depth. This is where f1 and this is O, right? Now here the object is, let's say, okay, this is f2 and this is 2f2. Okay, 2f2. Now what? It should pass through where? Through the focus, right? Now optic center pass. So what? They are moving away, right? As they are moving away, if you produce them further, what will be? They will going apart, right? So what you'll do? You'll produce them backward. Okay, produce them backward. When you produce them backward, where are they meeting? Right? Okay, so how the image is? Virtual, bigger, magnified, erect, right? And because of this, the convex lens is used as a magnifying lens. Okay, thank you.